Dear listeners, welcome back to the second part of the online international workshop, Differential Equations and Interdisciplinary Investigations. I present to your attention Professor Alexander Gorban. He will continue a course of lecture, Data-Driven Artificial Intelligence Problems and Ideas. Professor Gorban, you're welcome.
Okay, thank you a lot. Okay, my friends, nice to meet you again virtually. I am virtually yours. So today, my topic of my lecture is geometry and topology of data spaces. In some sense, we should solve a very strange problem. We have usually a finite data set in relatively high dimensional space, and we must restore geometry and topology. But which topological space we can expect? Discrete set, from the rigorous point of view, is just zero-dimensional, discrete set, nothing more. But we guess that behind this discrete set there is a space. And our topic today is how to reveal this space, how to describe this space, how to find this space which is behind the discrete data set. Okay, the two basic paradigms of data analysis. Well, two basic paradigms: statistical analysis, very deep and well developed at the beginning, first half of 20th century, and data modeling, much broader and not so rigorous, but also very popular. What's the difference? In statistical analysis, we always expect there is a probability distribution with rather good properties behind the data. And we have statistical hypotheses about data generation. The standard hypothesis is IID, famous IID. Independent, identically distributed data. And then somebody collected data for us from a set with given, maybe still unknown, but given existed probability distribution, and each data point is selected from the same set, from the same distribution, Nobody can guarantee this in reality. And then there's verification and falsification of hypotheses about hidden properties of data distribution. And this is very well developed science. You can find many books, but data modeling is so slightly softer. We have the universe of models. And the universe of models is in our hands. We create this universe. We should find the best model for data description. We know the universe, we know the fitting criteria, and then there are two types of analysis. Learning error. How good is our model for the data, and generalization of errors. We keep some data, don't include some data in learning, and then test on the still unknown data. Our model doesn't know this data, and we test. And then model verification and statistic is needed. But very simple statistics, like true, false, like proportion estimate. The first step of statistics, statistic proportional estimate. True, false, works, does not work. This is data modeling. And then for example, the simplest example, I prefer old example. See, is clustering. Clustering is data modeling. Nobody guarantees us that these clusters are not by chance. We just create clusters, it's hierarchical clusters, for example, as a model, and then verify, take new data, look, does this data point belong to the known cluster? So each data point create a new cluster and so on. And this is the simplest example of data modeling. Then there are, of course, you have heard many people speak about complexity. data complexity, struggle with complexity. There are two main approaches in our struggle with complexity. Originally, we have a very large data space with something interesting inside. We should reveal this interesting via model reduction, find a minimal space. This is one way. Another way, we should wait for data, more data, and expect that many data points will self-simplify the whole picture, or like statistical physics. In statistical physics, we have huge dimension, many particles, and altogether it's rather simple behavior, several macroscopic parameters. This self-simplification large dimension is great discovery of the end of 90s, beginning 20th century. Main persons have been Maxwell, Boltzmann, and Josiah Gibbs. So there are two ways. Now we will go the first way to minimal space with this interesting content. And the first attempt at this discovery was done by Carl Pearson. Somebody told me it may be Gauss, Carl Friedrich Gauss, long before Pearson did this, but in statistics, the first person was Carl Pearson. He published a paper on lines and planes of closest fit to systems of points in space, about best approximation lines to planes, three-dimensional planes, and so on in higher dimensional data space. And his first sentence, I so like this, I put it on a slide because it sounds absolutely modern. In many physical, statistical, and biological it's desirable to represent a data set in plane by best fitting straight line or plane. This is principal component analysis. Principal component analysis is the analysis of the best approximation of data by simple object. Pearson invented this. Well, this is what I should see. What this is, I recommend you classical book, text, something advanced textbook by Jalif, Principal Component Analysis. And how it works? It works very simple. We have data points. These green points are data. We find the best approximation line. Of course, we can notice that the best approximation line is also the line with maximal variance of projections. And sometimes this maximal variance people take as a definition. I don't like this trick in general, because best approximation can be generalized for many other approximants, non-linear, branching, very sophisticated. Maximal variance is not so good in that sense. So then it finds the best approximation lies the so-called first principal axis. At the same time, it minimizes if we take a spring from each data point to the line. This best fit line minimizes as the energy of these springs. Energetic metaphor is very important in our business today. Then the first principal axis. Then we subtract the projection and repeat. This iteration will give you principal components. Then we can generalize. Nobody tells us that the principal object should be a straight line. It could be just finite set. If you take a finite set, you'll find the famous k-means clustering. Here I took a Bismarck monument, just for fun. You can take anything. If you minimize the sum of square distances from the point to the object and fit the best position, we'll approximate data by their projections on the monument. This is a principal object, of course, jocularly principal object. K-means, people even call this approach principal points. K-means. Very simple. Approximation by a smaller finite set. Select several centers. attach data point to the closest center by a spring. Minimize energy. Repeat steps 2 and 3 until convergence. It always converges in finite number of steps. It was invented 56 years later after principal component analysis in 1956 by Guger Steinhaus. He studied some mathematical structures, not data analysis, then by Lloyd in 1957, then finally published it as cluster analysis for marketing purposes by McQueen a bit later. That is came in. There's also approximation of data by finite number of points. So now, after this brief introduction, we have two main first examples of data spaces, data approximation spaces. First is lines and planes. Second are just finite sets. First is principal component analysis. Second is principal points or k-means analysis. We can approximate by algebraic curves and surfaces. I attract your attention to very good books. This is special science. Let us have this nice set of points. What do we can try out? What we like this. What principal axis is that? What is better? Of course, this algebraic parable is better than first principal axis is black line. But can we go better? Yes, of course, we can go and we can take some overfitting lines that go through each point. Is not so good. That is, you can extend the space by values of additional functions and apply PCA. This is a deep theory behind, but you can understand that if you extend the number of the set of models instead of just of line, takes, for example, second order curves or third order curves, you can approximate better, but you need more data to test, to have good generalization ability. This is usually trade-off between the set of space of model, number of parameters in the space of model, and number of data points. Of course, for huge data, for huge model space, you can approximate everything, but you cannot generalize because we just feed noise. Just illustration, I like this illustration, non-linear happiness. These are countries. Each country is presented in 4-dimensional spaces by 4 numbers. Gross product per person, dollar per person, life expectancy years, infant mortality cases, tuberculosis incident cases, fraction, cases for 1,000, cases for 100,000. In years, almost 200 countries or United Nations countries, and year. And you can see that this, if you look at this data, you'll find this data are neither whole space data, nor just straight line. That's sort of two-horn, no, not parable, but something almost straight lines and nonlinear junctions, and again almost straight line. This is nonlinear. This is in our paper published. We call it nonlinear theory of happiness. Of course, this is again not absolutely seriously, but you can see that there are poor countries. Swaziland is on the one pole. And this branch of poor countries, everything is defined not by money. Money are not so important. Here, everything is defined by the physical quality of life, by infant mortality, this physical quality of life is highly correlated and doesn't depend much on the gross product is not very high here, not small, but everything is physical. And the rich country branch, the pole is Luxembourg. Yeah, United States, there's many countries, Qatar maybe, Sweden, Japan, Bahrain is already here, Saudi Arabia, and there is no linear junction. In non-linear junction, we can see Russia, we can see China, we can see Yemen, unfortunately not now, but some time ago it was, see Dominique, Chile, and so on. This is non-linear junction, and the trajectory of Russia, you would like to study the trajectory of Russia, you can look how Russia travels from 1989 to 2005. It's very interesting travel, first to poor hordes, then back to rich hordes, this sort of curve of travel. This is how principal curves can work. Now we'll just go ahead. How to find these principal curves? I propose, and no, we propose, we are not the only people, to use the elastic energy. This elastic energy was borrowed from splines. Splines, not mathematical splines. Mathematical theory of splines just borrowed this idea from the mechanical idea of splines. When people use it, this special plates, metallic rulers, and then approximate curve lines by these metallic strips, metallic rulers. This is a beam. They have not only elastic, they have bending energy. Of course, there are some points. We put this ruler through these points, and it itself minimizes the bending energy. Okay, that metaphor of elasticity. Now we should prepare something in between. K means absolutely flexible, no connection between points, and very rigid principal components, absolutely inflexible, no possibility to bend principal component. It's just elastic net. We have idea, so we have data points here, they are small black points, and we have nodes of elastic net. These nodes are connected by two types of spring: positive, attractive spring, and negative. Why do we need negative? Because negative spring allow us to emulate the bending energy. You see, if 3 points, you can look on any 3 points here. These points are connected. This point connected to this point by attractive, this by attraction, and the first and the third are connected by repulsive. And this allows us to keep these 3 points closer to a straight line, the bending energy. So there are elastic energy. Elastic energy consists of three, for this approximation, of 3 components. First, approximation, energy of approximation, average, mean square error. This is just mean square error. We have y, the node, and x, the data point, and the sum of squares of distance from the data point to the closest node is the energy of approximation. Then energy of stretching. 2 nodes where there exists a connection have some stretching energy. Distance is punished. And then the energy of bending. This is. And the approximation task is the minimization of sum of energy. When we minimize, we create the elastic net which approximates the data set. And this elastic net is a skeleton for the topology and geometry of data space. After that, we can take this elastic net, smooth somehow, and then work with these like geometric tools. The idea is we take the data set, we find the best approximation with minimization of this energy, and then we work with this approximation and analyze it as a data space. And this sum, usually lambda, usually stretching and bending moduli are some constant, but not compulsory, they can be variable. Assembling. We can assemble elastic net in many topological objects. For example, in a square. In a square, in a sphere. Oh, sorry, this is conflict of, maybe torus and so on, this conflict of computers. You various manifold topologies. It can be this, can be that, can be various globe. For this globe is this is just to tell you, this is globe of date of American elections, and this is presidential elections, and this is a globe. This is a president partial party win and opposition party win are presented in the globe, and this data analysis. This gives you always gave prediction, made only one mistake in Bush-Gore competition. All other predictions were perfect. We can use this data surface as a geographic information system. We can take this data surface approximated by the elastic net and visualize a very complex function, even, for example, a point density. Then we can, well, this is already the rather famous example of approximation of breast cancer. This is non-linear, this is elastic net. These points are cases of breast cancer, and this is just in internal coordinates below. In the internal coordinates, we see that various types of cancer are clustered on this projection. Nearby, there is a principal component projection. It is not so, the clusters are not so well articulated. This non-linear principal manifold, non-linear elastic net is much better. This is another, this is bladder cancer, and again, we have non-linear elastic map projection and the principal component. Again, you see clusters here and here is just improvement of principal component. And here is human tissues, the whole human here is. This is elastic map. We see different organs, different tissues, genome functioning different is well separated, and principal component not so well separated. Now to be a bit boring, we have to be a bit statistician. We should compare non-linear approximation with linear. And first question is, does non-linear give better approximation? Trivially, of course, yes. It is more flexible and the approximation is better. Here is, so two-dimensional map gives approximately as four-dimensional, five-dimensional principal components. Of course, this depends on a data set, because if data set is just point along a line, there will be no difference between linear and non-linear. Non-linear will be also along this line, and there will be no better. Everything will be on the first principal component. But this non-linear says breast cancer, bladder cancer, and normal tissues from the previous slides, always 4 or 5 linear. So we have compared 4-dimensional instead of 2 is rather big difference. So 5-dimensional. Then representation of distances. This is more sophisticated test. We can compare distances in the projection and distances in the reality. Preservation of distances is interesting. We should not confuse the far points. Far cases should be compared with far. Close, we should not create large distance between close cases. What can we do? This is distance after projection. This is a standard, even name it Shepherd's plot. This is a name it plot. So this is distance after projection. This is distance before projection. Of course, for small distances, this is a mess. Different, but what we like that small distances should not become large, and large distances should not become small. We should look on the for large distances. Everything should be more or less close to diagonal. Diagonal, this Russian Z, or just this special cross, is for elastic maps. We see elastic maps is very good in that sense. 10-dimensional principal components is compatible. Everything else is worse. Formal, this is very important test. And when you make modular reduction, make a step back. You should test approximation, trivial but important, and then representation of large distances, extremely important. And then there is a quality of distance mapping is measured by correlation between correlation coefficient, standard measure of two real variables. Correlation coefficients between distance before and after projection. You can see that elastic map, this network, elastic net, is more or less the same as 5-dimensional principal components. Or maybe sometimes it's 4-dimensional. The quality of distance mapping is very high for this nonlinear. It's good. Is this all? No, this is not all. The second, the fourth. So, point interest. The closest point should remain the closest point. So if the point in 10 dimensions, so it came in, K nearest point should remain more or less nearest. Maybe some of them will be not, but what is the percent of the nearest neighbors which remain nearest neighbors after model reduction? Crucial question. We should not, of course, we cannot guarantee that everything will be preserved, but this structure of the nearest neighbors should not be damaged too much. You see that the 2D here, nonlinear, two-dimensional nonlinear, is sometimes as 2-dimensional for bladder cancer, sometimes as the same as for breast cancer as 3-dimensional linear, sometimes for normal tissues 4-dimensional, also better. And this is the formal definition. Just what is the percent of the K nearest neighbors which remain nearest neighbors after projection on the reduced model, on the space of data. Good space of data, good model reduction should be good in that sense. And that is rather non-trivial property. All previous properties are somehow not related, not to anything, to data sense, to data meaning. We just take the data set and data set, project and compare. Now we know that our data set has some internal meanings. There are some classes. One type of, now for example here, this is normal tissue. There is a brain and there is liver, there is a heart and the muscles, and there is maybe whatever it is. There are meanings, and these compact classes, which are compact in the original space, should remain compact after projection. It's a non-trivial, and I recommend you to read the next slide specialist definition. For each label, we can calculate the average number of points with the same label in the k nearest neighbors, before and after. For example, we have from here we have tissues, we have brain. In brain we have these points. Of course, sometimes we find that there are several liver points. Some cells from liver close to brain, maybe just this with noises. The proportion in k nearest neighbors, k 10 nearest neighbors for brain is small. Then we project, the proportion is changed. So now we go to the maybe the most non-trivial part of my lecture. The previous part was principal components, you should know, classical statistics. K-means, you should know, two types of principal object. Then something intermediate, elastic nets for approximation of data that should be between K-means, which take into account only the approximation energy. When data point spring is connected by spring to the nearest neighbor, nearest node. And some sort of elasticity and bending energy that makes this elastic net not very large, elasticity, stretching, and close, not very far from a plane. The bending and stretching energy. And with this metaphor of mechanical metaphor, we create rather good approximation space. The software is free for, I will give you the link. Now we should mention that the question is why we take only this sort of manifolds, this local structure, local Euclidean structure. Why? Because nobody tells us that data should be situated along a smooth object. Maybe there could be some branching points. And then the question about principal graphs. The principal graph is a graph that approximates data. What should be? Of course, there should be approximation energy. Yeah, we guessed. Then we'll look on the slide. Then should be the bending energy, and then should be stretching, of course, and then should be branching energy. Because this branching will also be penalized. That we should take not so many branching, not so curve, not so much stretching, but with good approximation property. We introduce the notion of stars. Star is two stars, two neighbors, three stars has three neighbors, and so on. Then we say that what is the perfect branching? The perfect branching is the harmonic branching, when the central node is the average of the nearest, of the star. And this is energy of a node, branching energy. And of course, if branching energy is zero, this means that it's Laplace, a harmonic graph. And of course, this can be modeled by repulsing strings. Fine, we return. Then we create a primitive elastic graph. Each non-terminal nodes are elastic star. It's a graph energy is this number of edges and the sum of energy of edges, sum of energy of stars. And then pluriharmonic is a more complex that we can select stars, not all stars. We can take selected stars. For example, to model this plane lattice should take horizontal stars and vertical stars, not complete stars, not all connections. Then we should say the pluriharmonic map is when each node is the center, is the mean of these neighbors, pluriharmonic, this selected stars, is a pluriharmonic approximator. And this is instead of lines and planes. And then we have this grammar. We see the initial structure, generate and feed candidate topology, go ahead, penalty of total length, penalty of deviation from harmonicity, and this is implemented, it works. But how we can grow this graph? We should select the set of operations for growth. This is to grammar, the idea, new idea. Before we had the same ideas from manifolds, then for manifolds. Bending, stretching, now a new idea, complexity. Graph grows from the seed by a grammar. The simplest grammar is this, with only one. We have a set of operations. For example, add a node to a star or bisect a edge. Add a node to a star. This is operation. No, this is. We can add a node to a star. We can bisect an edge. And for each graph, we have several continuations. This graph can be continued to this, add a node to this, and to that. This graph can be continued to this, that, and that. This graph can be continued to this, and that. Very simple. We have two operations, and we can change our graph step by step by the operation of our grammar. Grammar is collection of operations, elementary operations. How it works? Just enjoy. We have a very simple data structure, just a dendrit. Of course, this data structure cannot be approximated by linear PCA, nothing interesting. Non-linear PCA, nothing interesting. Branching PCA, this is branching. And here is to create principal graphs, not principal lines, non-principal points, but principal graph. Of course, for simple structures, the principal graph will be a principal line or a principal just. Okay. There are three types of complexity. Geometric, how the principal object deviates from the ideal configuration, from a line, plane, from a harmonic graph, and so on. Structural complexity. How many elements has this graph? How many nodes, how many branching points, and so on. And constructional complexity. How many operations of grammar will be required to create this graph? And the question is when to stop. We should stop when the overall complexity becomes too large. Then the example from genetics. Well, first of all, if we take a gene as a text in this nucleotide language, four-letter alphabet, each gene can be cut in the pieces with sliding window, like several hundred nucleotides, and for each piece we can create the number of nucleotides, 4-dimensional space, the number of dinucleotides, 16-dimensional, the number of create, including the space of 4-dimensional. This is how many 4-dimensional, 4 nucleotides, words, 64-dimensional, and so on. So each text, even after we calculate the frequency of each word, small word in this like 400 dimension. First we have this large text, we cut it into medium-sized window. For each window, we find its representation in the frequencies of short words, and then therefore the big genetic text is embedded into medium-dimensional space. And then you can apply various principal component analysis, various methods. This is just example. This is three-dimensional. This is one bacterial genome. This is three-dimensional PCA plot of we should rotate to. This is graph Grammar's work, is this principal graph. And this is representation of the principal graph as a metro map. Of course, each tree can be represented as metro map. A very simple formalization, and each vertex is has a pie diagram with different clusters inside. Clusters is a type of reading frame. This is hierarchical cluster. It's a principal tree of the space of the data. Principal tree of this is a map of human tissues. Map from the genomic activity. Brain, you see, brain is very isolated, but the closest to brain is parathyroid and heart. Then adrenal, then thyroid. And this is prostate, seminal, thyroid, esophagus. This is the map. And when you look at this map, you can understand how expression of genes is where it's close, where it's distant, and so on. Gene expression, map of gene expression in different organs. We can study this as a map. And the last example, I like this example, because the method of principal graph suddenly, it was invented in 2007, but 2 years ago it was suddenly fit very well to huge new problem. Single cell omics is fantastic technology. I still don't understand it completely. Well, I understand something, but not completely. This is, we can take now, we, human, not me, take several thousand cells from an organism and measure gene activity in all these cells separately. Beforehand, we can measure average. Now we can measure all cells. So huge data set, each gene activity in thousands of cells. A huge matrix. What to do? This is absolutely non-trivial question. The question is, perhaps we can join the cells into trajectories, because cells are developing, and they are not just cells, they are trajections of cells in the they start, then born, then go, and then develop. And this is sometimes they diverge, trajections diverge, branching points, and so on. And this is a special time, branching time of development. They burn, then go, then selection, then selection, then selection of branching. And then mathematically, this is an example how branching time for this planarians are just worms. This is the map of the cells found in the single cell omics. You see, each point is a node. The pie diagrams is the types of genes active in this node. And these are just two branches selected for further analysis. Software, 4 things I told you, elastic maps, single cell analysis, and so on, is here. You can play with explanation. Conclusion, method of elastic maps, efficient. Principal manifold, it can work as a screen. Nonlinear data visualization works, therefore quality criteria. Pluriharmonic graphs work. Topological grammar and expectation maximization algorithm like k-means, but in more complicated environment work, and metro map also work. It works. These are some review publications. I recommend you to have a look. And software, please. And many more. Thank you a lot. Questions, please.
Thank you very much for your very interesting lecture. And of course, we have some questions for you. The first question is, can you explain again what do the E, I, and R mean in the elastic net?
What mean? Sorry? E, I, and R, elastic man, to run to the, this.
Yes.
Okay, E means, so this is for each H, you have three lists. List of nodes, lists of edges, and list of ribs. For each node is just a node. For each rib, for each edge, E, we have two vertices, two nodes, E0 and E1. For each rib, we have three nodes, R1, R0, and R2. These are, so this is functions. So in computer, you have, of course, how you represent, you have three sets indexed, nodes, edges, and ribs. For each, and they are connected. For each edge, you keep two nodes. For each rib, you keep three nodes. That's all. Rib is a set from the plain point of view. Rib is the set of three nodes connected with bending energy. You see, they are connected with bending energy. It means that for this rib, this is term in the total energy. Perhaps I answer. I have no more detailed answer. This is for. Okay.
Thank you. The next question. Suppose the given data is inside some compact set, and suppose one need to make extrapolation outside this set. What is the best way to do this from your point of view?
Wow, very good and very complicated question. So, first of all, of course, we should test value for this data set. Let us somehow take this, because we can look on the extension. We take some central part and test various models. There should be a sort of analysis, a sort of analytical property. The simplest is linear. You just take PCA and then extrapolate like principal component. Is it correct? No, it is not correct. It's never correct. Nothing is absolutely correct. But then you can say, oh, I prefer some nonlinear algebraic properties. For example, sort of, I personally prefer rational approximation like Padé approximation. Because rational approximation have rather good properties at infinity. Polynomial are terrible. Polynomial cannot be used for extrapolation. But sort of rational approximation can. You can take rational manifold using algebraic approximation theory and extend. Then you can guess, then some of my colleagues and me developed this sort of Carliman approximation, Carliman, please remember this name, Carliman analytic continuation formulas. And you can take Carliman formulas with some assumption about the area of analyticity. You can assume that the functions are analytic in strips, and then they have some, these formulas can be close to neural networks and so on. In some sense, right, some neural networks have these analytic continuation properties, but I should warn against blind use of neural networks approximator. You should understand what you do use. Okay, that's all.
Thank you, Professor Gorban. And the last question for you. How seldom do linear data spaces occur?
Sorry, how seldom?
Linear data space.
Non-linear, no, linear.
It writes in linear data spaces.
Okay, so what is the frequency of linear and non-linear? Should I compare how often I should use non-linear? Because first of all, the sort of intellectual hygiene, yes, is please start from linear. Never start from non-linear, first. Second, very often, I should say more than 50% cases, linear are sufficient. More than 50%. Then there is a very good, there's a family of good methods. I gave you these methods. I did not touch, I should tell you. There's one very popular method, autoencoders, neural autoencoders. This also creates a sort of principal manifold, but this is, we can discuss it separately. I cannot discuss everything in one lecture, but I should notice it. So, and more than 50% are linear. Like 30% are non-linear. Just from my experience, of course, this is experience, this is not scientific law. Okay?
Thank you, Professor Gorban. Again, thank you for your interesting lecture and for your answers. We are looking forward to your next lecture tomorrow. And now, dear listeners, we have a rest until 4 p.m. Moscow time.
Okay. Thank you very much for your attention, and thank you very much for very nice managing this lecture.
Thank you.
On, and then
Please turn on
you were on the broadcast.
I want to start the part.
Okay, Professor Bardos, can you hear me?
Yeah. On. Off or on the microphone?
Bardos from Paris, they brought in the university. This is the 10th lecture in the series. This is the lecture.
Dear Professor Bardos, please switch on your microphone.
On. That's it.
Okay, it's okay. Can you change your presentation in full screen mode?
I can change it in full screen now. Okay. Okay, I am on full screen.
Yes, it's okay. It's okay. You can start your lecture.
I can start my lecture. Okay, thanks a lot. Thanks for the patience of the organizer, for this team. Once again, very happy to be part of this web seminar. And I start my second talk, which is also on the Vlasov equation. Now, the first talk was derived to the following fact: try to connect a system of n classical or quantum particle with, let's say, one particle, means one going to n particle to a one non-linear, which was the Hartree equation, or when it's classical particle, go from n particle to one, which was the Vlasov. I insisted, and maybe you kept in mind, the fact that on this horizontal arrow in my diagram, there was no loss of reversibility. There was no question of entropy. And that's probably one of the good reasons why the problem, even if it's elaborate, is not so difficult. Now, if you do that and you want to describe some macroscopic phenomena, you will turn out to be in the real life, and in the real life, phenomena are not reversible. When you break a cup or glass, you cannot reconstruct it from scratch. So, let's say, and this will be the subject of my talk. I try to contribute to this field in collaboration with a guy from Nice, whose name is Nicolas Bess. Now, what is the quasi-linear approximation? The quasi-linear approximation It's considered a situation where the density of the electron, for instance, is in a box. Typical box would be a tokamak, for instance, like ITER, and then you are interested in the average intensity of the phenomena, and then that means the average over all the box. And of course, to make it more simpler for mathematicians, you replace your favorite tokamak by a periodic box, that the T at the power D in this formula, and you take the average in space. And then the question is to try to discuss that. Now, before that, I start with a baby model which do completely the opposite thing. Diffusion approximation has been around since Einstein and the Brownian motion, but it was systematically precise at the level of mathematics by Larsen and Keller around 1970. And the idea of Larsen and Keller was to put epsilon at the right place to get what you want. So, and also there is a very, now to understand that there's a very easy example is when you have d over dt, you have 1 over epsilon below the drift term, and you put a 1 over epsilon square below the relaxation term. To make it in the family of the Vlasov equation, I suggest to take as a relaxation term a Laplacian in V with a weight. And your favorite weight will be the Maxwellian, because to make the thing simple, it's 1 over omega, the gradient of V of omega of F. This is an example that I think is due to Landau himself, and that you can derive as an approximation of the Boltzmann equation if you think that electrons will have just, when they collide, would just have an effect at the level of the tangential collision. And also that the thing that have been worked a lot by Sasha Bobilev. Okay, now if you go back to the mathematics with this equation, first thing, it's a first order equation, and they're just derivatives, that's maximum principle. So it's a density, the solution will be a density which will positive bounded from above. And if you multiply by omega and integrate, you get to the balance between the energy and the dissipation of energy, which is very, very nice. Now, if you do that, you see that the gradient of F epsilon omega will go to 0. That's very easy, because I forgot the 1 over epsilon square, which should be here, 1 over epsilon square, and that forces this quantity to go to 0. When you have done that, if you integrate once with respect to V, since there is a gradient on V, this quantity disappears. The one there was a 1 over epsilon square, and you end up with the second equation, where you see that F epsilon, due to the first one here, will go to the density, which will be independent of the velocity over omega, omega being your favorite Maxwellian, or minus 1 over the Maxwellian, because there is a plus term. So that means that this V F epsilon will go to 0, but then epsilon also go to 0. So you have the limit of two quantities that go to 0. This has to be resolved. And in some sense, this is the gradient of the integral of this quantity. It's exactly what in physics you call a Fick law. Now you observe that in science you can move 1 over epsilon on the top. You will see that these two quantities, at least in the sense of distribution, they go to 0. The difference between the drift term and the advection and the damping term. So this difference going to 0, you use this equation to try to compute the limit. To do that, you try to find a function C such that if you take the scalar product with L epsilon, that will be a mathcal here also, then you will get the gradient of V of omega grad V, which will give V over omega. And that will tell you that the limit of V f epsilon can be exactly the gradient with respect to x of V rho over omega. Plot that in, and this way you got rid of the 1 over epsilon here, put that in the equation, and you get exactly the Laplacian. So that's a very simple model which works. And it works because you have this relaxation of energy, because this operator in some sense is like a Laplacian, it's coercive. Now it's a very classical example. You can have a lot of modulation of this example where you replace the omega of V by something that do not increase so fast for V going to infinity, because that's nice to have it here, V over modulo, that make this quantity in L2, for instance, and that make this quantity bounded. And it has been studied a lot recently, because if it's not so good, doesn't go so fast to infinity, it leads to some fractional diffusion. Well, this is a simple slide. It is the warm-up. Now I want to tell you that for the Vlasov, it does not work in general. That will be the next slide I want to deal with. Okay, so for do that, I will put some hypotheses on the Liouville equation, and I will go back to the scale, to the consequence, the scaling and the consequence of the Fick law. That will tell you why that make obstruction to the convergence of the rescale Liouville equation to the one I want to study, and then that's motivate the fact that I really need some randomness in the convergence and rather deal with stochastic equation, which will be the end of this section, and then that will be what I want to do today. And tomorrow I will attack the same problem with a different point of view, which is looking at completely deterministic phenomena, but for short time, and then leave you out of future generation the task of making the connection between the 2 points of view. Okay, so far so good. So, going in the detail, I will use the fact that the advection is in front of the advection term, there was a 1 over epsilon square. So the particle move like f of t, x minus t over epsilon square v. That would happen if there would be no electric field. There will be, if there is no electric field, what's happened? And I have to consider this quantity x minus t over epsilon square v modulo 2 pi, because I did that in a periodic box. I think a lot of things that I consider here could be moved to a bounded domain if you have a pure reflection of the particle on the boundary, and if you have some hypothesis on the ergodicity of the free flow with this thing. Okay, so since these functions are bounded, at least there is a notion of weak, they are bounded, they are positive, so you have a notion of weak convergence, let's say in the weak dual of this space, which is written here, so you can look at what will be a closure, a limit of a family of solution of this equation when epsilon goes to 0. Okay, now the second thing is that I will deal with the Liouville equation. Yesterday I also wrote several forms of the Liouville equation, and but it will be natural, keeping in mind the Vlasov, to assume that the vector field, they are potential, they are the gradient of things. Okay, in this present talk, I will take the initial data given independent of epsilon, and since it's really not the object today, I will assume that it is smooth. When it's smooth, that's the Vlasov equation that itself has been studied a lot with smooth initial data. It's known that in all dimensions up to 3, not so 4, no more 2 up to dimension 4, but up to 3 it's smooth, but the smoothness is not uniform. It may increase with the time, and since I rescale the equation, the estimates are not uniform. What is a natural estimate is that if you take the sup of the electric field for the Vlasov equation, take its first derivative in L infinity, and take the second derivative also in L infinity, but with a factor epsilon to compensate, one can assume for Vlasov that it is less than a constant, which depends just on the time or interval where you consider the problem. And that's what routine. Okay, so that more or less for the Liouville, I will assume the same type of hypothesis. Okay, so I go back, I try, keeping in mind what I have did in the very first baby model, I want to try to do the same thing. So I take the average over the torus of the density of particles, and I do that at any time. So if I integrate here, the average. Now this quantity in a periodic box can move the gradient with respect to x outside, and if I integrate with respect to velocity, with respect to position, excuse me, with the x, this goes away. This quantity goes away upon integration. So what remains again is the same thing. It's E epsilon, F epsilon over epsilon. Now, anticipating on what I would say yes, at the first slide, here the F epsilon will not be simply relaxed, but it will be driven by the advection flow. Since it's driven by the advection flow with a 1 over epsilon square, by a classical ergodic theorem, on a finite time, weakly, it will converge to a function which is independent of x. It's average over the domain. Now, E epsilon, it's a gradient. It's a gradient of x. If this one is independent of x, you take the gradient of E of x against something which is independent, then you average, means integrating with respect to x, something which just depends on x and which is periodic, that makes 0. So this goes to 0, this goes to 0. It's like in the model in the introduction. Now, what I would like to do, consider that like a Fick law, and like the people in physics find an equation of this form, which when we put it in the equation, will give me my favorite quasi-linear equation. And then immediately you see that there is an obstruction, a serious obstruction, which is that this equation, as a Liouville equation, will conserve in the dynamic all LP norm, in particular L2. Now, if you make the scalar product, that will give 0. Now you make the scalar product for the limit, which will be the quasi-linear approximation, as I like to call it, and you obtain that the energy will decay And this decay of energy is balanced by the dissipation of energy. This is a standard equation for the basic equation for the diffusion of heat. So you see there is a serious contradiction between the first equation and the second, which means that you cannot expect a strong convergence of this F epsilon to its weak limit. So in some sense, it's a thing which has to be reorganized. And this, we have to play with this weak convergence. Okay, now you can put that in a theorem, collect this observation in a theorem. The first thing I told you is that any cluster around for the topology, weak topology that you get from the above L infinity estimate will have the following property. Since with the ergodicity, it will do not depend anymore on V. It will depend on F. Epsilon will depend just on X and V. And if I go back 1 minute to the equation in blue, which are here number 5, you see that it will converge strongly if and only if the integral of the gradient of V epsilon against the gradient of epsilon integrate from 0 to t, capital E goes to 0. Otherwise, there will be a contradiction. Now, to understand, try to give a mathematical point of view in the physics. I want to see which room is left for weak convergence. So what I claim is that in the first slide, I gave some regularity of the vector field in X, not in time. So I write the point 3, which try to explain that just the only thing that may prevent the obstruction to convergence is that this field, the weakest thing is that the derivative with respect to time of F epsilon is bounded in any very, very weak space with some, and that epsilon dt of F epsilon goes to 0. If you have that, you end up with the fact that the dt of F epsilon will be 0, and that the Fick law is not the case you want to observe. It's because degenerate, it is 0. Now, I just make some comment on the proof. The first thing, the difference between the conservation and the non-conservation of energy comes from the fact that if you take the integral of the square and take its limit of the integral of the limit of the square by simple topology, Hilbert topology, is bigger than the weak limit integrated. I mean, so if you just use that, you find out exactly the first point. Now, which was the first point, which is here, or the second point, which is the strong convergence is equivalent to this quantity going to 0. That's trivial. Then, to try to mimic the proof that I proposed for the example of Larsen Keller, for the case where the thing works, I play the same game. I will multiply by epsilon x t phi of v, where phi of v is any scalar form, turn on the crank as I did, turn the inequality inspired by what I did at the baby model, and end up, if I control in the equation what comes in this derivative here, and if I control this derivative and with an epsilon, and if I control it in a very weak norm, then I can end up by that, what I was, the Fick law will be equal to 0 at the price I have to multiply by test function with a v here, which will cancel near 0. Don't need to check to keep in mind all the detail of this very naive computation, but keep in mind the idea, if you have good convergence, then you can converge to something multiplied by a function v of f and v, which will be 0, and then you end up with a diffusion which may be degenerate on all, acting on all these quantities. Okay, so that's what I said, that if you have regular expansion, regular space dependence, the obtention of a non-trivial diffusion require non-regular behavior with respect to time and a genuine multiscale, which will depend on t and t over epsilon squared. This is exactly what you find in some sense in physics textbook. And for the general, and if you don't think about just a Liouville equation, but you assume that the potential is given by the Poisson equation, which relates the density to the vector field, to the potential, and then to the vector field, which is the case of the genuine Vlasov equation, then you observe that the weak convergence of f epsilon tv will imply this quantity will imply the weak convergence of the density, let's say on any finite time, and if it implies the weak convergence of the density, since you solve the Poisson equation, that implies that the E epsilon of t and x will converge weakly. It is exactly what could be. It's a weak form of Landau damping, because it says that with the scaling, a vector field goes to 0, but it goes weakly to 0 due to time oscillation, which is not what you find when you read paper about the Landau damping. Landau damping will tell you when it happens that you have a strong convergence of the electric field. And here you just get for free the weak convergence, and that's the gap, which is the different reason why I call this type of problem very often a baby Landau damping. In my last talk, I will try to devote some time to giving more detail to this difference. Okay, so here I am. Now, just comment about the history, which is on this slide. I insist a lot on the fact that it's only in this setting that you will have a good equation if you have weak convergence. Doing mathematics on this type of problem has been done in a related problem. People have used the DEII formula, and the proof, in particular, you find it by Boltzmann, Lanford, Erdős, and Yao, which I mentioned yesterday. What is interesting is all these people, they used the DEII formula to generate something which is exactly a BBGKY hierarchy. So they need for the thing up to have it convergence of all terms of the BBGKY hierarchy. Now, yesterday, I talked a lot about the BBGKY hierarchy, but at the end of the day, I told you that if for the second marginal, which appears in the first term of the BBGKY hierarchy, you have a density F2 or ρ2, which is a product of two densities, then you just have, it's equivalent to have the equation, with the Hartree equation or the Hartree-Fock, and you have proven the convergence. What is striking is what you find in a series of paper of Poupeau and Vasseur in the French school, or Loper Vasseur in 204, and even later on, at the level of stochasticity, they do keep exactly the same root. Namely, they show that if in this hierarchy, you just have a factorization of the second, at the level of the second term of the Duhamel, then you get the convergence in the sense of probability or expectation. You cannot have strong convergence to get to the your favorite or the one you want, drift diffusion equation. Okay, so that's what I want to tell you. I try to convince you that to get for an equation from something which is reversible, you need some tool like randomness or average. And I told you that we just need to look at that at the second term of the Duhamel formula. So next, go down to there. So here's the Duhamel formula. You can write the formula, use the fact that if for the advection term, the operator epsilon 1 over epsilon square v nabla x, this is the generator of a group, and it's completely explicit. So you write it on the left-hand side of the equation and put on the right-hand side the E, the term E of sigma grad f of sigma. It will be exactly like it will be a linear differential equation. And then this term I will ignore in the rest of my talk, because if it is smooth, if I use the ergodicity of the torus, this goes to 0. If F0 is smooth, there are some very nice mixing property that will make it go to 0 faster. So I will ignore the first term. I end up and try to get a Fick law from this second. So now I need a Fick law, and since it's a weak convergence, what I really want to do is to look the action of this quantity, this will be what will be the term to determine, put it against f of v, and then to have it, I found out that the term which appears is, because I just apply one more time E epsilon of t, so the term that will play the role of the Fick law is this term. There is a 1 over epsilon square, because there's a 1 over epsilon in front of the electric field. I just reapplied E epsilon here, once E epsilon here. So we have 1 over epsilon t that came outside, and this term which corresponds to the 1 here. And then you get a very explicit form for what is in the integral, which is written on this line. You just see the action of the advection operator, you see the gradient of v, which is here, and the action of the above. Now, you have a t minus s over epsilon square, you make a change of variable, and you move to the next formula. Next formula, which gives exactly what will be in the Fick law, and you see that you get a term which is complicated, but it has 2 derivatives, one with respect to v, one with respect to v on this side, and the action of the electric field shifted from x plus sigma t to x and shifted in time. And this is what will be the analogous of the Fick law, that what hopefully will produce a diffusion matrix. So the main issue that you want to fix at this level is to analyze the diffusion matrix that may come from these animals here, and then justify the decorrelation between the f and this term. So that will be the thing. Okay, I hope I don't go too fast. And since I know that the thing oscillates in time, I told you at the beginning that they oscillate in time, I will start to make an explicit computation, assuming that the E epsilon, it has a time of correlation, which is like 1 over epsilon at the power beta. Now I compute it, when I put a k, I compute its Fourier coefficient. I compute its Fourier coefficient by integrating over the torus. Then it's called Ek. Since it's called A epsilon of T and K. Since it is the gradient of a potential, it's an IK. And I assume that this guy is an amplitude, F epsilon of T and K, which oscillated at a frequency 1 over epsilon. And with this hypothesis, which I assume, I put that in the formula for what would be the diffusion. Let's do that. And I end up with a term which is slightly complicated, but it is completely explicit with this hypothesis. And it's a sinus k minus a epsilon of 2 minus beta omega of k over epsilon square and kv 2 minus beta over epsilon square. That is a quantity which will give you more or less what is the right scaling for the diffusion, what are the difficulties. So if I want, the first thing I can do is to analyze this quantity in the sense of distribution. So if I analyze it, the same thing which was here, with a d epsilon of v, it reappears here against the gradient of v. I make the computation, and what happened, the phi k square appear outside. This is just because it's quadratic. And if I let this quantity go to 0, I will say that if phi k is less than 2, this will go to the integration against an hyperplane, which will be degenerate. And if it is equal to 2, it will go to the hyperplane moved by omega k over k. So you see, it's an integration on a thing which is of measure pk. So against smooth function, this will be equal to 0. This will be almost equal to 0. So that's the remark. And this computation is valid. It's easy to do. It's just a limit in the sense of distribution of the kernel, oscillating kernel, sinus S over epsilon, 1 over S, which is missing here, and that if beta is too big, all that will go to 0. That's just an example to let you feel what's happened when you oscillate more or not so, too much or too less. So I move for the rest of my talk to think where I will feel the oscillation. Feeling the oscillation, I will assume that the potential, the gradient of phi, is a random variable, why not? And as a random variable is defined on a probability space, that means that the expectation of f is the integration of f omega against the probability. And I make the standard hypothesis, which will be that the average is equal to 0, and that if you have a decorrelation length which is greater than a certain number t, then this two quantity turns out to be decorrelated, which means that the expectation of the product will be equal to 0. And if t minus s is less than epsilon square, then I use the fact that it is random, but is described modulo function of t minus s over epsilon square, but there is a small function here, by a function which depends just on the distance. It's called the homogeneity, and which oscillates at the value epsilon square. If I do that, I just immediately found that it's interesting to compute the Fourier transform of the A, and since it was a quantity which is essentially positive, there's a theorem of Bochner which says that the Fourier transform will be non-negative. The Fourier transform will also be symmetric, and that will appear in diffusion. With that, I can move to the next step. And the first thing I do, I compute the probability tensor, and then here there's a big difference. I just flashed very rapidly an example where there were pathology, and pathology was due that you integrate up to infinity. Now these two quantities, they become uncorrelated as soon as the distance between t minus epsilon square minus t is less than tau over epsilon square. So you just have the integration over a finite time, and that means that you will have a diffusion that will be not pathologic at all. It will be a nice diffusion involving the inverse transform of A, which is a probability quantity. All that will be positive. Very good. That's the first thing. The next thing, you use the decorrelation, and with the hypothesis about the decorrelation between the vector field, you find out that the operator A epsilon S and F epsilon, they are two random variables which are independent as soon as S is greater than t minus epsilon square. To do that, you just use the Duhamel formula one more. So I announced that there was the idea of Poupeau and Vasseur to just look at the second term. And in fact, if you look at the second term, you find out that what will be the expectation of everything, of what will be play the role of your Fick law, you can write it as the expectation of something that you will control, that will go from the diffusion tensor modulo something which is not exactly F epsilon as here, but it's F epsilon just shift from the time t to the time t minus 2 epsilon square. And for that you have a reminder. And the reminder, it's just computed on a finite time interval. It's a finite interval also in V space because we will use that in terms of distribution. And the computation, just counting the number of terms which are here, the 1 over epsilon and the change of variable make appear epsilon. So all that with the tangential regularity and nothing else will go to 0. So with that reminder is okay. For the decorrelation, you test on smooth function, and you have a little computation, but basically you will find out that you get a good diffusion. That's using the reg, and you end up with a theorem, which is the last theorem I want to write. You have X regular, but stock a family of vector fields which are regular on X, but stochastic in time, and the stochastic dependent on epsilon. In such a way, you have a function which describes the correlation between the two times of this vector field, which I call AK. Then its Fourier transform is non-negative. You have a nice diffusion equation, not with delta everywhere, which is symmetric, non-negative, and the expectation of all the F epsilon since it is the expectation of the solution of a Liouville equation will converge to a diffusion equation, which will be a diffusion on the set of V space with initial data, which was the average with respect to X. So here you have proven in some sense that that in this configuration, with the presence of randomness in the electric field, you have a necessary and sufficient condition, in some sense, at the level of physics to prove the validity of a quasi-linear approximation. I just add a comment to link with the problem that I did talk about yesterday. I start with the idea I go from particle to kinetic equation. I just did that yesterday. Today I tried to go from kinetic equation to macroscopic equation. That's the derivation which I explained. I tried to explain the role of the fact that we just deal with the second term of the hierarchy, BBGKY hierarchy, due to the point of view of Poupeau and Vasseur, or Lepère and Vasseur. Then it's also interesting to say that in the beginning of the century, there was some idea, beginning of the previous century, excuse me, there was some attempt to derive exactly the diffusion equation, the heat equation, directly from particle motion without using a kinetic in between. But to do that, the best way to do that was to try to describe the particle motion as solution of a Brownian motion. You have a potential which would be V or phi, which would be classical, and you have some random white noise behind that. If you do that, and it can be done, it's an alternative way, without going to the Vlasov, to get to the quasi-linear approximation. And it was known in the physics literature, and let's say there's quite a big literature in plasma physics. I just quote one paper where people compare what they do coming from the Vlasov equation to the wave diffusion, what they could do coming from the particle motion with a white noise to the drift diffusion, and they found a nice relation between the two quantities which describe the randomness either at the level of the kinetic equation, as I was in my talk, or at the level of the random noise from the beginning. Okay, my time is gone. Thank you for your patience.
And we have some questions for you. First question, how principle for R's? Sorry?
Yeah, maybe I can see the participant in the question now, okay?
So the first question is, how principle for R's to assume that initial function independent on epsilon, page 5?
Okay, it's not at all essential. You can relax the hypothesis on the initial data. But on the other hand, it's more important for me, it was more important to try to find conditions under which, even if the initial data is smooth, it goes to a real diffusion equation than the opposite way. And this doesn't appear. The point is that the singularity of the bad behavior, we'll say, of the initial data is not present in the proof here, because what is important is the decorrelation between the electric field and the solution at the time t. At this point, due to this property, this lemma of Vasseur and Poupeau, this only what happened when in a small time between t and t minus epsilon squared tau, which is important. And in the effect at the beginning of the UML formula, the action of the free group on F epsilon disappear also. So a message from that is rather to enforce, to insist on the oscillation of the potential or the vector field with respect to the time, which is the degree of oscillation in time.
And one more question for you. In what sense is the integral in form?
Say it again, in one sense. In what sense?
In what sense is the integral in Formula 16 understood?
Which is the Formula 16? I go back. It's, oh yeah, that's, I can go back to here. Okay, very good. Formula 16. 13, 14, 15. Where is the 16? I just say that it's just a way to say that f, define here just the expectation of a random variable, and to say that I have a function which depends on a random variable, and it means that it depends on omega, and it's integrated on the probability on a space omega with a tribe and with a probability by formula of this type. Okay?
Okay, thank you very much, Professor Bardos. Thank you for your lecture and for your answers. We are looking forward to your next lecture tomorrow. And now, dear listeners, we have a break until 5 p.m. Moscow times.
Okay, so in 5 p.m. I'll be back to listen to the other talk. Thanks for your patience. Great.
Thank you.
Thank you. Okay.
Oh, good evening.
Good evening. Yeah, I'm coming for a dog. You are going to.
Is it okay? I
Sure.
have a few minutes.
Okay. Is this?
Okay. Oh, I'm
Yeah.
glad to see you. Okay.
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 Okay. You can start. Very good. I'll be back. I'll be back in a minute.
Hello.
Okay. So is it possible to start?
Yes, dear listeners, the next speaker is Professor Vyacheslav Grines
Okay.
from National
Thank
Research
you.
University, and he will, with his second lecture on the interrelation of regular and chaotic dynamics with topology of an ambient manifold. Professor
Okay.
Grines?
Thank you. Thank you. Okay. So it's today I am glad to start next lecture, second lecture.
Yes. Can you please turn on your presentation?
Okay. You see my presentation? Do you see?
Not yet.
Not yet. Okay. Not yet. Now?
Still not.
Still not? Okay, okay. I try to delete, okay.
Yes, we can see your screen.
No. Okay, okay. Now?
Yes.
Do you see my lecture at this moment?
Yes.
Okay. Thank you. Thank you. Sorry. So I would like to present our book where it's possible to find all definitions that I use in my lectures, and there is some part in this book where exists section devoted to the main concept of topology which uses in dynamical system. So if you want, you can find my book and find references. Okay. So I recall that we consider Morse-Smale diffeomorphism, dynamics of such diffeomorphism. Let Mn is a orientable smooth closed manifold of dimension n. Definition. Diffeomorphism F, Mn to Mn is a Morse-Smale diffeom if its non-wandering set omega F consists of finite number of hyperbolic periodic points and stable and unstable manifolds of different points from this non-wandering set have transversal intersection. Yesterday we discussed this concept, and during this lecture I recall this concept. Who wants? Okay, so continue. Today I will consider so-called gradient-like diffeomorphism. Morse-Smale diffeomorphism is called gradient-like if condition intersection is not equal empty for hyperbolic periodic points PQ implies that dimension WSP less than dimension WSQ. Remark. When n is equal 3, a Morse-Smale diffeomorphism is gradient-like if and only if the two-dimensional and one-dimensional invariant manifolds of its different self points do not intersect. Let us emphasize that two-dimensional invariant manifolds of different saddle points of gradient-like diffeomorphism may have a non-empty intersection along heteroclinic curves. So I suggest to look at the next picture to understand what is mean gradient-like diffeomorphism. So we have arbitrary Morse-Smale diffeomorphism, and we yesterday, I hope, recognized that stable and unstable manifolds of different saddle periodic points can have intersection. On left picture, we have intersection one-dimensional separatrice, one-dimensional manifolds with two-dimensional manifolds. Okay, this intersection is heteroclinic points or heteroclinic orbits in some sense. On right picture, we also see intersection stable and unstable manifolds, but this intersection belongs two-dimensional invariant manifolds, and it's very important with compact heteroclinic curves and non-compact and compact. So both cases are possible. So it's the only such intersection are possible for Morse-Smale diffeomorphism, but we say that our Morse-Smale diffeomorphism is gradient-like diffeomorphism. If left picture, it is not possible. Okay, it's very important to understand at this moment. So we admit right pictures, not admit left pictures. Okay, and our result that in this case we can also explain topology of origin manifolds, three-dimensional original manifolds, which admits gradient-like diffeomorphism. So it's our aim of our lecture, goal of our lecture, and I try to explain it. Yesterday, yesterday, I recall that if we did not admit right picture, we get that our manifold, we obtain that our manifolds is product connected sum of S2 times S1, a few copies S2 times S1, a number of these copies completely defined by number of saddles and sinks and souls. So it's very important. Today, I also give some classification of manifolds which admits more small, but gradient-like diffeomorphism, more small, okay? So topology, our aim is topology of ambient manifolds M3, admitting gradient-like diffeomorphism. Let G, the number, we also saw this number yesterday, which is fraction. K is number of saddles, L is number of sinks and souls, plus 2 divided by 2. Okay? So our theorem, if M3 admits gradient-like diffeomorphism with tame bunches of one-dimensional separatrices of saddles, then the manifold M3 admits the Hegardt splitting of genus G. So if we look at this theorem, at this moment, I hope we all understand what is mean gradient-like diffeomorphism, because it's usually more small diffeomorphism, but without heteroclinic points. But we don't know what is mean time bunches of one-dimensional separatrices. So I would like to explain what is mean the first, and the second, I recall what is mean Hegardt splitting of genus G. So now we try to explain these concepts time bunches and concepts of Hegardt splitting of genus G. So I recall what is mean handle body. Any genus zero handle body is homeomorphic to free ball, B free. I have no picture free ball, but I hope that all people understand what is mean free ball. Free ball is handle body of genus G is equal 0. A genus 1 handle body is homeomorphic to B2 times S1. So it means solid torus. Okay? B2 two-dimensional disk, S1 is a circle. And this product is called solid torus. Handle body of genus G, more than one, may be obtained by taking the boundary connected sum of collection G of solid tori. So we have a few copies of solid tori and organized connected sum. Okay, surface, boundary surfaces. So you see picture of handle body. So it's possible to say it's solid tori, and if you consider, for example, pretzel, so it's possible to say what is mean solid pretzel, but I hope that you understand what is mean handle body. So this picture is enough for understanding. What is mean Hegardt decomposition? If we consider two copies of torus and gluing these copies some homeomorphism boundary of two copies, we get new manifolds, which is called Hegardt. So I explain more exactly. Hegardt splitting. Let V and W be handle bodies of genus G. You can imagine two copies of genus G. And let F be an orientation reversing homeomorphism from the boundary of V to the boundary of W. By gluing V to W along F, we obtain the compact oriented free manifolds without boundary. And it's denoted M3 is equal V gluing along F, W. Now there is remarkable result. Every close orientable free manifold may be so obtained. It's this representation is not unique. It is not similar to Kneser-Milnor theorem, where we say about unique decomposition as 2 times S1 and irreducible manifolds. Here we can many for done decomposition, but however, it's very important, it's right by red color, every closed orientable free manifold may be so obtained. The decomposition of a free in 2 handle bodies is called a Hegardt splitting, and their common boundary H is called the Hegardt surface of the splitting. Okay, so we already can formulate our theorem almost, but it's necessary to explain. So I come back. Theorem: if a free admits gradient-like diffeomorphism with tame bunches of one-dimensional separations of saddles, then manifold M3 admits the Hegardt splitting of genus G. Conclusion you already understand. It's remain to explain what is mean time bunches. Okay, so I suggest to understand this concept. Let M3 be gradient-like diffeomorphism, and L omega be the bunch of all unstable one-dimensional separatrices of saddles who contain omega in their closure. I said yesterday, if the one-dimensional separatrice doesn't contain interclinic intersection, its asymptotic direction is some point omega. So we consider all separatrices which go to something omega. A bunch of omega is so, so we write L omega be the bunch of all unstable one-dimensional separatrices of saddle which contain omega in their closure. Is it clear that it's possible to explain L alpha for some source? Now, a very important concept for me today. A bunch of omega is called time if there is homeomorphism Ws omega to are free, because if we have omega, we have stable manifolds for this omega, for these things. It's some ball which homeomorphic to a free, are free. So we say that bunch is time if we exist homeomorphism psi which maps this bunch to linear bunch, to some family of some race starting from O for any separatrice L belong to omega in the opposite case. But if we have no such homeomorphism, we call such bunch wild. Okay, so time if right picture at its time, but it's there exists situation that is not possible to construct such homeomorphism for bunch of separatrices. Look at next picture. The Bruner Fox example. De Bruner and Fox in 1960 constructed an example of wild collection of arcs in a free, which each arc is time, but bunch is not time. Such collection is called mildly wild. So you see that each separatrices are good. However, it's not possible, you see from this picture, it's not possible to find homeomorphism which maps such picture to linear array, linear bunch. Okay. Mildly wild bunch in dynamics. Using this example and methods of realization of Morse-Weil diffeomorphism, this methods was obtained by me, Christian Bonatti, my former graduate student Olga Pachinko, that we can construct different examples of Morse-Weil diffeomorphism. In some sense, we have complete topological classification, three-dimensional Morse-Smale diffeomorphism at this moment. It was finished recently. Olga Pachinko constructed such example that we have two bunches which are that is not time, but each separatrice is good. So it's very interesting example. So it's example of Morse-Smale gradient-like diffeomorphism in this picture. Okay. So the mind of one of the main question of topological classification, such examples, this problem was solved at this moment. But now we study what manifolds admits such diffeomorphism, okay, with such phase portrait. This picture is possible on S3, and S3 admits Hegardt decomposition. So it's don't contradict our theory, okay? So we introduce the concept all time bunch of separatrices. If L omega consists of exactly one separatrice L, then timeness of L omega is equivalent to existence of a smooth closed free ball such that separatrice L intersects boundary of this ball only in one point. This principle was proved by Harold Griffiths Rasse. So in right picture, it's good time curve, but in left picture, any boundary of any ball, separatrice intersects minimum in 3 points. So this separatrice is widely embedded. So we give such definition. Bunch L omega, so we come back to Morse-Smale diffeomorphism, gradient-like, and consider bunch L omega. And bunch L omega is called almost time free if exists smooth closed free ball such that omega belongs to interior B omega, and each separatrice intersects boundary of disk of ball only 1 point. Okay, so it's good situation. It's similar with example which I explained before, example by Pachinko. Okay, each separatrice intersects ball in only 1 point. It's our requirement in the next. Okay, so we give definition bunch L omega is time. If we come back to our theorem, if M3 admits gradient-like diffeomorphism with time bunches of time bunches, now we know what is mean time bunches. It means that if separatrices go to sync, there exists some ball that each separatrice intersects with ball only in 1 point. Okay, so it's the main condition for class gradient-like diffeomorphism. We don't consider arbitrary gradient-like diffeomorphism, but we consider gradient diffeomorphism with requirement that all bunches, one-dimensional trees of saddles, are time, okay, are time. And in this case, we get, we say, where we will prove that this manifolds admits Hegardt decomposition, splitting of general G. Okay. So now we understand all concepts. I hope we understand them. And we now will discuss how we get Hegardt decomposition. Why it's interesting for us? Because you will see that you understand the dynamics of gradient-like diffeomorphism. It's very important that arbitrary Morse-Smale gradient-like diffeomorphism have some dynamics which possible to describe very simply way. let's start. Global dynamics of gradient-like diffeomorphism. One-dimensional attractor and repeller. Don't hurry. Let F be a Morse-Smale diffeomorphism on free manifolds. At this moment, it's not necessarily gradient-like. Let us denote by omega plus, omega minus the set of all sinks sources. By sigma plus, sigma minus the set of all saddle points having one-dimensional, unstable, stable invariant manifolds. By L plus, L minus, the union of the unstable, stable one-dimensional separatrices. Look at the picture. The green picture. We have sink omega 1, sink omega 2. We have saddle sigma 1, and we can see the separatrices with saddle, and they go to one of separatrices go to sink omega 1, another omega 2. Yellow picture, similar. We have one-dimensional continuum which consists in stable separatrices of sigma 2, and one separatrices go in for negative iteration to alpha 2, another to alpha 1. Okay? We set A union omega plus, L plus, sigma plus. A omega minus, L minus, sigma minus. It is possible to prove, but it's almost obvious. For example, you can imagine, for example, flow with such sinks and sources. So you see, if we consider neighborhoods of P plus, and if you consider ball which surround omega 2, omega 1, and some handle which join these balls, we get some surface, boundary of this handle body will be surface, which is surface without contact for flow. But we cannot say for diffeomorphism without contact, so it's possible to believe that this handle body iterate to inside for positive. And for yellow picture, it's also iteration go to inside for negative iteration of diffeomorphism. So it means that green curves are A is attractor, but another for repeller is union of, I forgot color. Brown continuum is repeller. Okay, but it's possible to prove. It's necessary to prove. But at this moment, we would like to believe to me. Then number G is exactly the number G which we introduce in our theorem. G is number of saddles minus number of sinked source plus 2 divided by 2. Where stands where this two straight line is cardinality. Recall that K is sigma plus sigma minus, and L is omega plus union omega minus. Okay? So we have attract and repel. So what I would like to emphasize, if we have arbitrary Morse-Smale diffeomorphism, we can consider one-dimensional separatrices at their closure unstable, and one-stable separatrices saddles, stable separatrices, and their closure. And we get two continuum. One continuum is attractor, another continuum is repeller, and our orbits go from neighborhoods of repeller to neighborhoods of attractor. So it's very beautiful situation if we consider any Morse-Smale diffeomorphism. Dynamics can be represented as attractor repeller pair, retractor repeller. It's very beautiful result. So at this moment we already can see our theorem, because you see green handle body and yellow handle body, and if it's clear that our manifolds is Hegardt decomposition, which is surface of this decomposition. Hegardt surface is homeomorphic to boundary of yellow or green handle body. But it's only a first view. Now I try to prove this fact, because I draw a very simple picture, but there exist very, very complicated pictures. However, the result is true. Okay, let's continue. Let's continue, my friends. So number characteristic for one-dimensional attract and repel. Set G plus, sigma plus minus omega plus plus 1. And G minus is sigma minus minus omega minus plus 1. Okay, so we have, if you remember, two pictures, so we can consider numbers, sinks, saddles, plus 1, and so with statement. For any more small diffeomorphism, M3 to M3, G plus is equal G minus and equal G. So it was beautiful result. I very shortly try to explain proof. According to Shoup and Sullivan, a more small diffeomorphism induces in all homologic groups a isomorphism whose Eigenvalue are root of unity. Thus, there is an integer k such that f power k leaves per fk fixed, all periodic points fixed. And restriction power fk to WP preserves the orientation WP for any point P. And 1 is the only Eigenvalue of isomorphism induced by fk on homology, because if of Eigenvalue is root of unity, so some power, all Eigenvalue are unit. Okay. Step 2. Apply the Lefschetz formula to fk. We get sum of indexes of periodic P, the number minus dimension dim WP, this is index of point P. But at this moment it's not very important, but very important with formula. It's possible to calculate. Right, it's Euler characteristic of manifolds from right side, where T is the traces of map induced by fk on the if homology group. By assumption on K, T coincides with the if Betty number, and the alternate sum of these numbers is Euler characteristic. But we know that three-dimensional case Euler characteristic is 0. So we get, it's possible to calculate that this sum is equal 0. Hence, this sum is equal to this subtraction is equal to this. That is G plus is equal G minus. As G plus is equal such number, we get G minus is equal this, and then G plus G minus is equal to G, so we get that G plus and G minus is equal G. So we prove the fact that it was almost obvious in the picture. It's genus of this handle body the same, but it's necessary to prove exactly. We prove it using by algebraic topology. Now we would like to explain neighborhoods of attractor and repeller. And don't hurry, you see, we have more small diffeo, we consider saddles, and we consider separatrices. And at this moment, very important that we have no heteroclinic point. So one-dimensional separatrices go to some omega, and all separatrices, asymptotic direction is some sinc, and for another saddles, each stable separatrix go to some source. So now we can formulate theorem. Where is a neighborhood P plus P minus of the set A such that P plus is F compressed, is go to inside after iteration. And double S sigma plus consists of exactly one two-dimensional closed disk for each saddle point sigma plus. Okay, so it's also very important. We have for us, so we have some handle body with this intersection is disk, and each separatrice go to sinc, so to source, and intersection is some disk, because it's very important. And this theorem we also use that our bunches are good, are time bunches. Okay. Construction P plus. Now I explain what we do indeed. It follows from suggestion of almost time bunches of one-dimensional separatrices. So I formulated theorem, and now I explain how we prove it. I already explained it, but I repeat. It follows from suggestion of almost time bunches of one-dimensional separatrices, L plus, but where exists an F-compressed domain B plus, made of M plus balls, which is a neighborhood of omega plus, and such that each separatrice L intersects the B plus and unique point. You remember definition of time bunch. Choose a tubular neighborhood H plus of L plus minus in B plus. In picture I speak about this handle, okay, tube, good tube which intersects with separatrice by disk. Choose a tubular neighborhood H plus such that P plus is F compressed when P plus is handle body, but it's also not so obvious. It's necessary to apply Lyapunov function and another methodics, but geometrically it's clear that it's possible to do. Okay. Then P plus is handle body of genus G. Indeed, P plus has homotopic time of circular complex with omega plus 0 cells and sigma plus 1 cells. When beta 0 minus beta 1 is equal omega plus minus sigma plus, where beta 0, beta 1 are the Betty numbers of a plus. It's very easy to check. Take account of that B0 is equal 1 and B1 is the genus of P plus, we get the genus of P plus equal G plus. But G plus, if you remember, is equal G. So we constructed very beautiful neighborhoods, handle body, which surround attractor and repeller, one-dimensional continuum attractor and one continuum repeller. Okay, I would like that you look at this picture. So we constructed with yellow and blue handle bodies and calculated genus. This genus is calculated using by numbers sinc and using by numbers source and saddles. So very beautiful result. Okay. So now we can almost finish our theorem. Splitting lemma for product at G multiply segment. It's very important fact of this theory. I would like to say that all results which I presented now was obtained by me and my colleagues Evgeny Jujoma, and Vladislav Medvedev. And this topological lemma, it's K moment in this theory. And it was proved and published in journal Mathematiический сборник in Russian, I think in 2003 year, and its proof, size of this proof, 15 pages. And that moment it seemed that this lemma rather obvious. However, they never found proof of this topological lemma, and we discussed this question with Matveyev and Dmitry Viktorovich Anosov, and Francois Laudenbach, topologist, and later, and it's became clear that this lemma not proved, never, but it's more understanding for topologies. So formulation of lemma. So it's in some sense it's generalization such theorem. If we consider annals on the plane, annals between two circles, and consider any closed curve with divided with annals on two parts, any parts is also annals. If you try to prove this theorem, you see that is not so obvious. Similar to Jordan theorem. In three-dimensional case, we can consider annals between two spheres, and also consider some sphere we delete with annals on two parts. We claim that these parts are homeomorphic. And here is generalization. Let Q be an orientable surface with following properties. Q is smoothly embedded to interior of manifold. H is equal SG multiplied by segment, where SG is orientable surface of genus G. In this picture, we consider torus. Okay. Q doesn't bound and open domain. We require it. Then the closure of each component of set H minus Q is homeomorphic to H. So if we consider product as G by segment, and if we consider some surface which embedded in this product such way that is divided with product to parts, which both parts are homeomorphic. It's beautiful topological fact. And proof is not trivial. Okay, so we now will use this fact to prove Hegar decomposition. Okay. Now my pictures are schemes. Denoted by S plus S minus when boundary of handle body P plus P minus. Okay, so you see on the picture attractor, repeller, and it means that I consider this picture attractor, repeller. But now I schematically draw attractor, repeller, and P plus, P minus handle body. It follows from above that S plus and S minus are smooth orientable closed surface of genus G. You agree? Because we prove it. As the set L omega, L alpha are time for any omega alpha, then both sets P plus minus A, P minus are homeomorphic to the product, whereas G is orientable surface of genus G. Is the main place where we use the concept of time bunch. Okay, because we say that if we delete attractor, we get product surface. So there exists foliation on the parallel, in some sense, surfaces, two-dimensional, which parallel to boundary. Okay. Choose a number n such that Fn S minus belongs to int plus. Okay. Because A is a attractor, so we have some iteration. After some iteration, because boundary is compact, we get such inclusion. And put S minus n, Fn S minus. Okay, you see this picture, beautiful picture. So it's clear that this part of manifolds is product, because it was product. I take diffeomorphism, so I get also product. But I can, at this moment, I cannot show that this also. Now I would like to prove that this part also remain product. So I will use my lemma, topological lemma. Okay. Choose a surface Sn plus, which belongs to plus minus A, such that Sn plus is a leaf. Sn plus is a leaf, because I said that it's product, which appropriates to some value Tn in the product. So it's leaf. Second, Sn minus belongs to the interior of closed domain, which is homomorphic to the product and bounded by Sn plus and S plus. Okay, look at this picture. But our lemma, this part, is also product. It follows from our lemma. So, by splitting lemma, the closed set bounded by Sn plus and Sn minus also is homomorphic to the product. It's very important. This part, Sn minus, where is not written. Not by the Sn minus, Sn plus. Okay. By splitting lemma closed set bounded by Sn plus, it is Sn plus, it's Sn minus, and it is product. When the closed set Mn plus, Mn minus, yeah, already I explained M minus. And this part, Mn plus, also, which contains the attractor A, the repeller A, are bounded by surfaces N minus, is a handled body of genus G. Consequently, M3 is union Mn plus, Mn minus is Hegardt splitting of genus G. Okay, so I explain once more. This part is product because it's diffeomorphism, and here we get product by our lemma, and it's product because it's also product. It's divided on two part, which also product of the same genus. So it's very good, homomorphic. So it's clear that we get Hegardt decomposition of our manifolds. So our theorem completely proved. So I hope that I explained the idea of this proof. And you can see this proof in our book, there is part devoted to this problem about interrelation between topology of manifolds and diffeomorphism which given on these manifolds. Finish. Thank you very much for your attention.
Thank you very much, Professor Grines, for a lecture. And we have a question for you. The question is, what are the applications of Morse-Smale diffeomorphisms?
Oh, any dynamics, any models which can describe the more described by system differential equation, by system of differential equations which contains finite number periodic solution and finite number singularities, if Jacob matrix all Eigenvalue in singularities not real part is not equal to 0, and usually, and periodic points also are hyperbolic. It's possible to explain using by Poincaré map. You can see closed curve, can see the disk which transversal with periodic, and we get map, Poincaré map, and all Eigenvalue doesn't equal to 1 modular. Okay, it's so in this case we get more small flow. If we consider time 1 diffeomorphism, we can obtain more small diffeo. If we consider some flow which has section, global section, on this global section we have more small diffeo. But you understand, you know, I am sure, that model kinetic, magnetic field, and in physics models, radiotechnic, and in very many applications, you know, you can take Andronov Haykin book. There are very many models, and these models are more small flows, and they depend on some parameters, and if we change parameters, we transmit from one more small to another more small flow. It is very important to study bifurcation parameters. Okay, so all systems which have regular dynamics may be described by more small dynamical system. But where exist system and models, Lorentz models and another, they possess chaotic dynamics, but it's absolutely another history. And tomorrow I explain a situation when appear chaotic dynamics. Also, if we know how manifolds, fundamental groups, and other things, and action of induced diffeomorphism and fundamental groups of manifolds. So application of this theory absolutely using in absolutely many different applications. Okay.
Thank you very much for such
yes.
a detailed answer.
Mm-hmm. Thank you for your question.
Here is another question. It is, why the term gradient-like?
Why should what?
Why, I guess, why to use the term gradient-like?
Okay, because for flows, gradient-like means that our flow have no closed trajectories, and in some sense, and it's generally, and so it's in some sense generalization, because if we consider flow which is gradient of some function, you understand that this flow doesn't contain closed trajectories, and behavior which we go from source to saddles, from saddles to sinks. So very simple dynamics. We go from higher level to below level. So it's reason why this system named gradient-like. Because if we have heteroclinic intersection, is not gradient-like. Dynamics more complicated. Okay. Because if we consider gradient-like flow, and consider times 1 diffeomorphism of this flow, we get exactly gradient-like diffeomorphism. Okay. In this diffeomorphism will not contain heteroclinic points. So I explain how it's appear this concept. If you consider gradient-like flow, gradient flow, yes, it's easy to understand that they doesn't contain closed trajectories. If we consider times 1 map, it's clear to see that there appear heteroclinic points. Okay. Oh, I finished. What?
I guess your presentation
Yes,
is
understand. I explained to you. Okay.
Yes, thank you very much, Professor Grines. And I guess if our audience has
But who
another
asked
question,
me? Where are you from? Who asked me?
it was anonymous question.
Anonymous. Oh, okay.
But
okay.
the audience can join the discussion session after the lecture, so they can ask you.
Okay. Thank you.
Thank you very much.
Thank you very much. That's all. Okay.
Dear audience, we now have a break for 7 minutes till 6 p.m. Moscow time.
Good afternoon, dear colleagues. We are going to start the last lecture in today's program. The mini class called Reaction-diffusion equations in biology and medicine will be given by Professor Vitaly Volpert, senior researcher in National Center for Scientific Research, France and Lyon University. He is also collaborating with the Rouen University. Professor Volpert, you're welcome.
Good evening, and thank you for this presentation. And the title of the second lecture is Stability and Instability of Solutions of Reaction-diffusion Equations. And of course, stability theory, one of the most interesting developed theories in mathematics and in applications. And here I give three examples among the most well-known examples of instability of solutions. At the left, it is an elastic rod. When there is a force applied to this rod is sufficiently large, then it changes its form because of the instability of this previous form and the bifurcation of this new form. Another well-known example is in the middle figure related to convection, natural convection in fluid. If we take a fluid, it's an everyday experiment. We heat it from below, and then this fluid loses its stability and begins to move. And the last example here is in the right figure. I mentioned it in my first lecture, related to the patterns at the animal skin. Of course, these examples concern different models, and only one, the last one is related to reaction diffusion model, but we consider some other examples sometime later. So I will begin with giving some very simple, very trivial examples of stability of solutions, just to introduce this understanding, what means stability of solutions and how it is determined. Then we'll consider some brief introduction to the stability theory. And then basically the main part of this lecture will consider stability or instability of three different types of solutions. Constant solutions, meaning that they don't depend on the space variable, stability of waves, and stability of pulses. And all the time I will give different examples, mainly in biological and biomedical applications. So probably the most simple, trivial, and clear examples of stability and instability, I mentioned it in the first lecture. If you have just one ordinary differential equation with its stationary points as shown here in the figure, the function f equals 0. For example, in the left figure, there are two zeros. So the left figure is unstable. Why it is unstable? Because if you consider the initial condition here, a small positive number, so then the function f of u is positive here, du dt derivative is positive. So the solution will grow and it will not return to the stationary point. This is an example of instability. And this is another example of stability. If you take an initial condition here, small positive number, f of u is negative, the derivative du dt is negative, the solution will decrease and converge to 0. So these two trivial examples explain the notion of stability. And the next example here for two ordinary differential equations introduce already what we need in what follows, eigenvalues, how stability is related to eigenvalues. Of course, all this is very well known, very simple, but it explains rather well the situation. So we have a linear system of two ordinary differential equations. We have this matrix of the coefficients. We can easily find eigenvalues and eigenvectors. We can construct the solution written here. And obviously, if lambda 1 and lambda 2, the eigenvalues of this matrix, if they have negative real parts, then the solution will converge to 0. in this case 0 is a stable solution of this problem. If one of these eigenvalues has a positive real part, then the corresponding exponential will grow, the solution will grow, so the solution will not converge to zero solution, so zero the relation between eigenvalues and stability, which is that if the eigenvalues of our linearized problem have negative real parts, then the solution is stable. And if at least one of the eigenvalues has a positive real part, then the solution is unstable. So of course, these are trivial examples, but the main ideas, the main results, of course, if we don't discuss strict, rigorous mathematical formulations, but on the level of description, similar results remain valid for much more general problems. And here, next several slides, I will give a very short introduction to this stability theory. And this time we will consider this equation, semi-linear parabolic equation, sometimes also called reaction-diffusion equations, in a bounded domain with some boundary conditions. And here I take zero boundary conditions, zero boundary condition, with some initial condition. So this is called initial boundary value problem. And we suppose that this initial boundary value problem has a stationary solution. What means stationary solution? It's a solution of this equation which does not depend on time. Therefore, we obtain this boundary value problem written here with the same boundary condition, but of course there is no initial condition because there is no time. It is a stationary solution. So now we can define stability or instability of the stationary solution Wx as solution of this initial boundary value problem. So what we do, we consider this initial boundary value problem, the same equation, the same boundary conditions, but our initial condition now, we take the stationary solution Wx and we add a small perturbation. Then if for any small perturbation phi of x, the solution of this initial boundary value problem converges to Wx, then this stationary solution is asymptotically stable with respect to small perturbations. If there is a small perturbation phi of x such that the solution will not converge to the stationary solution, then the stationary solution is unstable. Of course, I cannot give precise definitions now, but I think the idea is clear. So we have introduced the notion of stability. Now, similar to these previous simple examples, we need to consider the eigenvalues of the linearized problem. So this is what our nonlinear operator, which corresponds to the right-hand side of our equation, nonlinear operator. This is linearized operator, which is the Laplace operator is the same, but here it is different. We differentiate the function f with respect to this variable u, substitute our stationary solution. This is multiplied then by this perturbation v. So this is the linearized operator, and then we consider the eigenvalue problem. LV equals lambda v. Of course, we need to consider also the boundary conditions. And the result is formulated exactly as before when we consider the simple examples, that if all eigenvalues of these eigenvalue problems have negative real parts, then the stationary solution is stable. If there is an eigenvalue with a positive real part, then the stationary solution is unstable. Of course, in this very short lecture, it's impossible to give and explain all details. The result I have formulated now is valid only for bounded domains with a sufficiently smooth boundary. If we consider unbounded domains, in particular reaction diffusion waves, we'll discuss them later, then the situation can be a little bit different. And in particular, we need to consider in this case what is called essential spectrum. But we will not discuss it in detail. So now we continue our program. We have introduced the notions of stability and instability. We have understood that the stability is determined by eigenvalues of the linearized problem. Now we will apply these results to study different situations, different stationary solutions. And we begin with the simplest type of stationary solutions, constant solutions, constant in the sense that they do not depend on the space variable. And here, right away, I will illustrate this and present as example what is called Turing structures or dissipative structures. And it is a very interesting example of this type of stability or instability of constant solutions. Turing published this work in 1952, and now it is one of the most famous works in mathematical biology and also beyond mathematical biology. So what is the idea and what is the question started by Alan Turing in this work? So we consider the reaction diffusion system. It can be two equations, it can be more equations, but not one equation. One equation is not sufficient. We consider two equations like that in some interval like that with some boundary conditions. All that it's not very important. What we assume that this system of equations has a constant stationary solution. For simplicity, I take that it's u equals 0, v equals 0. What it means? It means that f of 0, 0 equals 0, g equals 0. So, sorry. The boundary conditions are also satisfied. So, of course, this is a solution, a stationary solution of this problem. Okay, so now we have these diffusion terms here. Let us forget for a moment about diffusion. Then we have a system of two ordinary differential equations, and u equals 0, v equals 0 is a stationary solution, a stationary point of this ordinary differential system of equations. Suppose it's our assumption that this stationary solution is stable. I repeat, we assume that the stationary solution without diffusion is stable. So the question asked by Turing is whether it is possible that the solution which is stable without diffusion becomes unstable with diffusion. The question is not trivial, and it is in some sense counterintuitive, because when we deal with heat equation, diffusion equation, we are used to the idea that diffusion acts to stabilize solutions. Here it appears that it can be opposite, and this is very interesting. So, and in fact, the calculations behind are very simple. So here we have this system of two ordinary differential equations, well, the corresponding matrix of the linearized system, and we assume that both eigenvalues of this matrix have negative real parts. This is our assumption. Then we consider our reaction diffusion system. We linearize about the same solution 0, 0. We obtain this eigenvalue problem. Also very simple. We can solve it explicitly. Either we apply the Fourier transform, or we use solutions in the form of like that, like sine or cosine. We substitute it in this equation. We obtain these algebraic equations. And in fact, again, now the matrix becomes like that it is almost the same as before, except for now here we have two additional diagonal terms related to the diffusion terms. In the first equation, the diffusion term was this d. So when we substitute sinus kx, it gives us minus d1 k2, and in the second equation minus d2 k2. Okay, so we say that this matrix is stable, both eigenvalues are negative. So what happens with this matrix now? So the first idea is to say that when we subtract something from the main diagonal, the eigenvalues become even less, so they should remain negative. And this is true if diffusion coefficients are equal to each other. If they are equal to each other, indeed, we just subtract something from the eigenvalues and they remain negative. But it appears, and this is very strange on the first glance, but then simple calculation, of course, we can do it, that if the diffusion coefficients are different from each other, then even if we subtract them from the main diagonal, then under some conditions on the coefficients of the matrix, it becomes unstable. So for different diffusion coefficients, the matrix can become unstable. It is possible that it will have one negative and one positive eigenvalue. And as a result of that, it's a simple calculation for the eigenvalues of 2 by 2 matrix. So I don't show it here, but everybody can do it in 5 minutes. So what is the conclusion? The conclusion is that diffusion can destabilize our stationary solution, and this instability of solutions, it is called Turing instability, leads to bifurcations of solutions, bifurcation of spatial structures. They are often also called Turing structures or dissipative structures. And now it appears that this simple construction has many applications, in particular in mathematical biology, and one of the most spectacular is the application, I already mentioned that, the application to this kind of problems, how to describe patterns on animal skin. There are many works in this area, and it is possible to reproduce very accurately these patterns. In particular, you see here some examples. There are some other examples from Murray books with the zebra, with giraffe. These are also very beautiful examples from the book by Heinz Meinhardt, The Algorithmic Beauty of Seashells. There are many, many other examples. Of course, I cannot give all these details now, but it's really very interesting to read and to look at all these examples. But these ideas, of course, of this Turing instability, they go much beyond this some examples, for example, for animal skins. There are many other applications, and I will show a couple of them. Here, the same ideas are applied to the prey-predator model, also a very popular topic in mathematical biology. Here, well, it's a little bit more complex. It is considered some integral terms. Now, for us in this short presentation, it's not important, but you see there are many, many different patterns which can appear as a result of this instability. And the last example for this kind of instability of stationary solutions, it concerns neural field models. It's also a very, very broad and very interesting domain. In fact, it concerns the way how our brain deals with the information or with different activities. It appears that all types of our activity is accompanied by the propagation of periodic waves in the brain cortex. Here you see some experiments. There are some, this is a cross-section of the brain. There are these red dots, these are electrodes, so they measure electric potential, and each electrode, so of course the the original data. It's kind of a complex oscillation there. It's not necessary to produce some data treatment. After that, you see this kind of this periodic time oscillations for each electrode. But if you compare different electrodes, these time oscillations are a little bit shifted. So it means that this wave comes to the next electrode with some time delay. It means that we observe here propagation of these periodic waves. And then there are many modeling works, in particular these neural field models, which allow to study this phenomena. And it appears that before that these waves can bifurcate from a constant stationary solution as a result of this instability. It's also a very interesting subject, but of course we cannot discuss it in more detail now. So the next part of this lecture concerns stability of waves and pulses. Here again we need to begin with some definitions and some comments. So as before, we consider this reaction-diffusion equation. Yesterday I introduced this type of solutions, reaction-diffusion waves, Wx minus Ct. This function Wx satisfies this second order ordinary differential equation. What is important to note here? Suppose that Wx is a solution of this equation. Since this equation does not explicitly depend on the space variable, so we can consider all functions Wx plus h with all real h. All of these functions will be also solutions of these equations. It's quite obvious observation, but it is important, and this is called that this solution is invariant with respect to translation in space. Why it is important? Because exactly because of this property, the linearized operator has a zero eigenvalue, and this has some consequences for stability of solutions. So what we have here, we need to introduce some additional definition. Stability, it is called stability with shift. So we have this equation, we have this linearized operator. And then we can verify that this linearized operator has a zero eigenvalue. Indeed, how to do it? It's very simple. If we differentiate this equation with respect to x, we'll obtain exactly this expression where v equals w prime. So again, differentiation of this equation gives us L w prime equals 0. This means that the operator L has a zero eigenvalue and w prime is the corresponding eigenfunction. So the previous stability result I presented several minutes before. In this result, we assumed that all eigenvalues are in the left half plane. And then we have stability. Here we have zero eigenvalues, so we cannot directly apply this result, but there is a theory of reaction-diffusion waves. It is quite well developed, and we know what happens in this case. In this case, this wave is what is called asymptotically stable with shift. What means with shift? This means that this solution u of x and t, when we consider this initial value problem on the whole axis, now it's not initial boundary, but initial value problem, Cauchy problem. So we take our stationary solution, Wx, our wave solution, sorry, we take a small perturbation, and then the solution u of x and t converges not to Wx minus Ct, but Wx minus Ct plus h for some h. So we have a shifted solution converges to a shifted wave. This is called asymptotic stability with shift. So after this definition, we can now we will study stability of waves, and of course there are many results. It's a very interesting, very developed area. I will give only one result based on what is called Crane-Rootman theorem. It's a very useful and very interesting theorem, which I will formulate now. So we consider this second order linear elliptic operator, scale operator, with some boundary conditions are not very important. So this operator, we consider the eigenvalue problem. So this Crane-Rootman theorem affirms that the eigenvalue with the maximal real part, it is called principal eigenvalue. The eigenvalue with the maximal real part is real, simple, and the corresponding eigenfunction is positive. Again, I underline this again, I repeat, because this is important, not only for this lecture, but in general, very nice theorem. So the principal eigenvalue is real, simple, the corresponding eigenfunction is positive, and moreover, there are no other positive eigenfunctions. This means that other eigenvalues, except for the principal eigenvalue, cannot have positive eigenfunction. And we'll use it right now to study stability of waves. A short remark here, this theorem is valid for scalar problems in bounded domains. If we consider not scalar equation, but systems of equations, usually this result is not applicable, but there is some class of systems, I will mention it before, for which this result is applicable. And if we consider unbounded domains, we should also again introduce the essential spectrum and take it into account. Here we will assume that the essential spectrum lies in the left half plane and it does not influence stability of solutions. Now with this result we can easily prove, we can easily study stability of waves. So just several lines, just one slide, a very simple construction. So we have this equation, we have a solution Wx of this equation. As we did before, we denote U equal Wx and we differentiate this equation number 1. We obtain the equation number 2 after the differentiation, and we use this notation U equals W prime x. The linearized operator written here, it's exactly the same expression as here. So as we already discussed before, it is easy to see from here that 0 is an eigenvalue of this operator, and the corresponding eigenfunction is W prime. But Wx is our solution. Our solution is like that. W prime is the eigenfunction, and since the solution is monotonically increasing, it can be also monotonically decreasing, because all this can be, if we multiply by -1, it doesn't change anything. So the solution is monotonically increasing, so our eigenfunction is positive. And now we apply this theorem, Crane-Rootman theorem, which says that the only positive eigenfunction corresponds to the principal eigenvalue. Therefore, 0 is the principal eigenvalue. 0 is the eigenvalue with the maximal real part, and all other spectrum lies in the left half plane. Therefore, from this we conclude that our wave is stable. Of course, here we need to be more precise, we need to give some more details. In particular, as I explained before, it can be stability with shift because of the 0 eigenvalue, but there are some details which we cannot discuss now. So we see that this theorem allows us to prove the stability of waves, so local asymptotic stability of reaction diffusion waves. Also, with some a little bit more development, we can prove that these solutions, these reaction diffusion waves, are not only locally stable, but they are also globally stable. And in this slide, I will explain very briefly again how this result on the global stability of reaction diffusion waves can be used to determine the wave speed. It's also a very interesting and very useful result. So let me explain. Here again, we see our equation here. We should recall that C, the wave speed, is unknown. And in applied problems, I mentioned it yesterday, it can be sometimes very important to find the value of the speed, in particular in combustion problems. It's a speed of wave flame propagation and many other applications. So if we take, and there are different methods to determine wave speed, so I present here one of these methods. So if we take this equation, we can express C obviously in this form from this equation. So if we know Wx, the solution of our equation, of course, we find C, the wave speed. But usually we don't know the exact solution of the equation, so this representation of the wave speed is basically useless. But it appears that if we substitute here in the right-hand side in this formula, instead of the unknown wave, if we substitute some test function, I call here it rho of x. So in the same expression, we substitute this some test function here, test function here. We take here the supremum with respect to x of this expression, here the infimum with respect to x, and it appears that the wave speed is between these two expressions, between the maximum, supremum, and between the infimum. And then, if we continue this construction, if we take here where we have infimum with respect to x, if we take now supremum with respect to all test functions, and in the second expression the infimum with respect to all test functions, we obtain the exact formula for the wave speed. And then this approach can be used to determine, to evaluate, to estimate the wave speed in different applications. And I'm not sure that I will have enough time, but I plan to show it how it is used in some applications. Okay, now I will a little bit go faster. So we used Crane-Rootman theorem to prove stability of waves, and we use that the fact that the wave was a monotone function with respect to x. Therefore, here W prime was positive, and of course here we use that Wx is a monotone function. If Wx is not a monotone function, then u of x is not positive, then the eigenfunction corresponding to the zero eigenvalue changes sign, and we conclude that 0 is not the principal eigenvalue, and then in this case there is an eigenvalue with a positive real part. So it's some sense opposite result. So before we proved if our W of x is a monotone function, then the principal eigenvalue is positive and the solution is stable. Now W of x is not monotone function, W prime and the principal eigenvalue is not positive, therefore 0 is not the principal eigenvalue, then there is a positive eigenvalue and the solution is unstable. So our conclusion, our next theorem, so non-monotone waves and also pulses, because pulses, a solution like that is non-monotone solution. So for this problem, these solutions are unstable. So again, with this theorem, we obtain a very, as a direct consequence, very useful result about this time instability of waves. All these results about the existence of waves. Yesterday we discussed the existence of waves for the scalar equation. Today, stability of waves and the wave speed. All these results can be generalized for some classes of reaction diffusion systems of equation. For general systems, they are not valid, but there is a class of systems, they are called monotone systems, for which this result is valid. So these systems are characterized by these conditions. So if we take the Jacobian matrix of the nonlinearity, the off-diagonal elements of this matrix are non-negative. Such systems are called monotone systems. And this is a class of systems for which the maximum principle is applicable. So in general, maximum principle is not applicable for systems of equations, but for such systems of equations it is applicable. And all these results we discussed yesterday and today about existence and stability of waves, maybe you remember that in the bistable case, we proved the existence of a unique wave for the unique value of speed. In the monostable case, we proved the existence for all values of speed for larger than or equal to some minimal speed. Here, but for the scalar equations, these existence results are very simple phase space analysis. For systems of equations, it becomes much more complex, but the results remain valid about the existence of wave, about the stability, about the minimax representation of the wave speed. And then there are many different applications of these results in different fields, and I very briefly show because not much time. So there are many applications, chemical kinetics in combustion. I will not stop on that here. Here the slide shows there's a very well-known problem. It is called system of competition of species in population dynamics. It is not directly monotone. These derivatives are negative, but by change of variables, it can be reduced to monotone systems. So like that, we prove existence and stability of waves. And then I very briefly, I will show two biomedical applications. The first one is atherosclerosis and the second one, blood coagulation. So we don't have time to discuss what is atherosclerosis. Very shortly, it's a chronic inflammation of blood vessel walls. And the simplest model we developed many years ago is this two ordinary differential equations and partial differential equations for the cells, monocytes participating in these inflammatory reactions, and for these activatory cytokines. And what is interesting here is that depending on parameters, namely depending on the level of cholesterol in blood, there are three different situations in this monostable case, bistable case, and we can use now all these mathematical theories we discussed before about the existence and stability of waves. So we have here the existence and stability of waves, which describe atherosclerosis. What means describe atherosclerosis? Describe this chronic inflammation, or in the other words, describe, you see it here, it's another type of modeling. Here you see this atherosclerotic plaques, these green nasty things here. So these atherosclerotic plaques in the blood vessel wall, they grow as reaction diffusion waves according to these results I just showed just before. And the next application also very shortly about blood coagulation. Unfortunately, again, we cannot discuss it in detail. But and one of these components, yes.
Volpert, there was some problems with sound. Can you please repeat the last sentence?
Already about blood coagulation.
Yes.
Right. So blood coagulation is a very complex process. Basically, it involves platelet aggregation and coagulation cascade. This means chemical reactions in blood plasma. So I will very briefly discuss only this one, these chemical reactions. They are very complex. We cannot discuss all that in detail, but in some models we obtain these reaction diffusion systems of equations. In this particular model, there are 6 equations. It appears that this system satisfies our condition. It is a monotone system of equations. So we can apply all these results about existence of waves, stability of waves, but also existence of pulses. We can also prove for such kind of systems existence and instability of pulses. This is also important because though these pulses are unstable, but they are important in these applications because they determine the class of initial conditions. But okay, we will not discuss it now. And also here it's one of the examples where the speed of propagation is very important because the speed of propagation of this coagulation wave, it determines where blood coagulation in our body occurs normally. If the speed the speed of this wave is too low, this corresponds to hemophilia, insufficient blood coagulation. If the speed of this wave propagation is too large, this corresponds to thrombosis. Both of them, of course, are very, very dangerous. And here we can study the speed of propagation with all these methods. Also, another interesting aspect of this model is that how it happens in our body. Of course, blood coagulation occurs in blood vessels, and in blood vessels, of course, there is blood flow. So we should consider how this reaction diffusion wave propagates inside blood vessels, taking into account the blood flow. So schematically it is shown here. This is the blood vessel. So if the vessel wall is damaged, so this blood coagulation starts here at the lower wall, and it propagates, this wave propagates upwards. This is how this blood coagulation occurs in our body, but at the same time there is blood flow coming here like that, and it changes this wave propagation, and it is shown here. So instead of a straight wave like that, so the form of this wave, the form of the clot becomes deformed because of the blood flow. And here, just to finish with this topic, just numerical simulations, and also these are experimental results. These are numerical simulations already with platelets, but this blue, you see this blue, it's fibrin, it's this reaction diffusion wave, how it propagates, this blue one, how this clot grows. Okay, so in the remaining 2 minutes, I will give 2 examples of instabilities and bifurcation of waves. So we discussed stability of waves. What happens is if the waves are unstable, so then some other solutions can bifurcate, and this slide here shows several examples of bifurcation of reaction diffusion waves. So what is here? So we consider a circular. We consider a circular cylinder here. There's a plane wave propagating here. This plane wave can lose its stability, and in this case, there are these spiral waves appear here. So these waves begin to rotate like that, or they can behave like that, or like that, and so on. So it's a very interesting and very rich nonlinear dynamics of reaction diffusion waves. which is observed when these waves lose their stability. And the last example, I showed you in the first lecture yesterday, we have a propagation of a system of two waves here. So the first wave, and then the second wave. Here in this example, they are stable, but what happens if they are not stable? And one example is shown here in my last slide. So I will return to this example tomorrow in the applications to mathematical immunology, because this model comes from the mathematical immunology. But now, only shortly, we see these waves propagating one after another with different speeds. Because of time delay, which is here, these waves can lose their stability, and there are different patterns can appear here, periodic or sometimes aperiodic. So I skip conclusions and I stop on this. Thank you for your attention.
Thanks a lot for your lecture. We've got some questions. The first one, could you provide references regarding the neural field modeling from slide 14?
Yes, right. So there are many works, really many works devoted to this field. I can provide references. If the person who asks this question contacts me, I can send papers or references.
Okay, thank you. And also have another question. How does connect stability targa you mentioned with spectral stability?
Sorry, I did not understand stability.
Yes,
Repeat,
I also don't understand. I think there is some mistake. How does connect stability targa you mentioned with
targa? What means targa?
I don't know. It seems like there is some mistake, or I don't know.
Well, sorry, I'm not sure how to answer this question because I don't understand what means targa. But well, I can only say that local stability of solutions is related to the spectrum, to the spectral properties, in particular to the eigenvalues and the assertion spectrum. If the person who asked this question can explain, then I can answer more precisely. Otherwise, we can do it maybe later.
Okay, thank you. Maybe the person who asked this question will connect with you during discussions. Thank you again for your lecture. Now will be break. Now will be break till 7 p.m. Moscow time, and I would like to remind to listeners and lecturers that there will be discussions at 7 p.m. and you can join them using the link in questions and answers or in the program.
Okay, thank you. Thank you for all listeners. Bye.